Welcome. In this video, we're going to discuss an example of induction where we have to guess at a formula and then prove that that guess is correct with mathematical induction. So what does this problem say? So we're supposed to conjecture, take our guess at a formula for the sum of the first n Fibonacci numbers with even indices, so the even numbered Fibonacci numbers, and we're supposed to prove our formula works using mathematical induction. So in other words, in notation, we need to find the sum of f2, f4, all the way up to f2n. This is kind of a real-life scenario that mathematicians are in. We want to find a formula for some expression, and we don't know it to begin with. We have to maybe just try some things. We have to guess. We have to do a little bit of brainstorming to figure out what expression might be equal to this one in a closed form. And then to verify that our guess is correct, we'll use induction to do so. So let's give this a try. I suppose we should just start by writing down some of the Fibonacci numbers. So f1 is equal to 1, f2 is equal to 1 as well, and then the Fibonacci numbers start from there and growing, adding the previous 2 to get the next one. So f3 is 2, f4 is 3, f5 is 5 itself, f6 is 8, and then finally f7 is 13. We'll stop there. We'll try to notice what we can with these numbers. So what we want to do is think about what happens when we add up the even numbered Fibonacci numbers. So I'll grab a different pen color. For f2, the only number that we've got so far in my sum is f2, and that sums up to 1. And then once we hit f4, then we can take f2 and add f4. That would be the even sum up to 4. So that would be the number 4. And next, f6. At that point, we'd have f2 plus f4 plus f6. And that would be 4 plus 8, which is 12. So maybe we can notice a pattern with what we've written down so far on the screen. Pause the video right now and see if you can come up with a guess at what this formula might be. Okay, so after looking, you might notice that, okay, if we take f2 and we add 1, we get f3. But that pattern continues. If we take the f2 plus f4 going up to f4 and we add 1, then we get f5. And similarly, the 12 adds 1 to give us the very next Fibonacci number. So let's write down our guess. I'm going to guess that the even summed Fibonacci numbers, f2 plus f4 plus all the way up to f2 sub n, is 1 more than the very next Fibonacci number. Or in other words, the very next Fibonacci number, f2n plus 1, minus 1, right? If we take the number f2n plus 1 and subtract 1 from that number, then we'll get what we're guessing here. And we're going to go about trying to prove this guess is correct by mathematical induction. So I'm going to label this statement as P sub n. P sub n is true or false, and we'll try to show that it's true for every n value bigger than or equal to 1. So we'll give ourselves some space, we'll scroll down, and we'll try to prove that that guess is correct. By induction, we need our base case to begin with, so we'll plug in the n equaled 1 case. We've really already done that above, but formally we should include a proper base case, so we're going to do that. We're going to show that P sub 1 is true. So when we plug in 1 above to this formula that's right here, on the left-hand side, we just get the very first term, f sub 2. And f sub 2, of course, is 1. And then on the other side of our equation, we get f sub 2n plus 1. So when n is 1, we'd have 2 times 1 plus 1, so that would be f3, which is equal to 2, but then we would subtract 1. So we have f3 minus 1, which does give us the number 1. So the base case checks out. 2 minus 1 is 1. Now let's move along to our inductive step. So in the inductive step, we want to show that the nth case implies the n plus 1th case. So we want to show that p sub n implies p sub n plus 1, and we want to do this for every n value bigger than or equal to 1. Okay, so we'll scroll down, we'll just give ourselves a little bit more space to operate here. What we would like to have accomplished here is f sub 2 plus f sub 4 all the way up to f sub 2n, and then including the very next term as well, f sub 2n plus 2. We want that to end up being equal to the very next Fibonacci number, which is f sub 2n plus 3 minus 1. So the very next Fibonacci number minus 1. We need to connect the chain between those two expressions of equality. So our chain of equality can start by manipulating the first n terms that we see here. Let's just write that in red notation so that we can easily see the substitution that we're making. So by p sub n, all of that red stuff is going to change to the very next Fibonacci number after 2n, so f sub 2n plus 1 minus 1. And then we drag across the f2n plus 1 from above. And now we're very close to what we wanted. We wanted it to be equal to this, and p sub n itself told us that, if you do this for n terms, you get the very next Fibonacci number minus 1. We just have to show that this works with adding on the next even Fibonacci number as well. But if we look closely, we actually have two consecutive Fibonacci numbers. This number right here and this number right here form two consecutive Fibonacci numbers because whatever number 2n plus 1 is, the very next number is 2n plus 1 plus 1. But that's the number that's right here. It's 2n plus 2. So now the definition of the Fibonacci numbers finishes off our problem exactly the way that we wanted it to be finished off. So to remind you again, the definition when I'm writing DEF here is referring back to the definition of the Fibonacci numbers, which is right here, that tells you that the previous two Fibonacci numbers in the sequence give you the very next one. And that's exactly what we had below, where we were writing the previous two Fibonacci numbers by the definition give you the very next Fibonacci number. And this completes our inductive step. The base case got the check mark, the inductive step got the check mark, the induction is complete, and our guess was in fact correct.